Okay. So, yeah, second half, a kind of completely different topic, really. So, this was what I showed you at the start. What we did then was introduction to all this. We did gas kinetic effects. I introduced it to disjoining pressure. We'll need the disjoining pressure again here, but we're also now going to think about thermal fluctuations. Okay, so another small scale effect so that it's, again, Navier-Stokes plus some nano stuff. That's the idea. So there's many, many places where we care about the breakup of very thin films of liquid. So, for example, in emulsions, their stability depends on the ability of thin films to resist drops coalescing. In biology, people are interested in dry out of the layer of liquid coating the eye. In manufacturing, you might want to break up the film. You might want to not break up the film. You might want to make sure it's stable. And in playgrounds, you can break up soap bubbles. So what I'm going to be thinking about is applicable to kind of all these situations, but this is the one I'm going to be thinking about. That's a thin film of liquid on a solid. And the reason is, I like that because I know where the solid is. Whereas in these, I don't know where the bottom is, so it's a bit harder. But in principle, the same ideas apply. So if we go back 20 years ago or so, there's some really kind of pioneering experiments on the breakup of very thin films of liquid done by a German group. And what they did is, I mean, you should understand, to see the nanoscale is kind of possible, but to see the dynamics of what's going on there is typically not. Because if you want to visualize something on a nanometer, you can't do it with a temporal resolution of nanoseconds. It's much slower. What they had is extremely high viscosity liquids, many thousands of times larger than water. They coat a solid with it, and then they watch it break up using AFM. And the point is, it breaks up so slowly that they can scan, AFM scan, and create a video, basically. So this is the video. What you see here is these black spots. These are where a hole forms in the film. So these thin films are unstable somehow, and once they become unstable, these holes open up, and the eventual state will be some drops. But that will take some time. What I'm interested in today is just a very simple question of how long does it take for one hole to form? So as I mentioned, the problem is we can't usually see these flows, so we don't understand how they work. So again, trying to motivate why we might want to do modelling and computation rather than just do an experiment. Okay, so again, I'm going to split the talk into two. I'm going to talk for some period of time about some kind of educational bit, and then I'm going to go like this again and fire through my research at the end. Or maybe this will be better time, we'll see. Okay, so the tool which we're going to use as a kind of experiment is molecular dynamics, which is not an area I'm an expert in, but we have collaborators who do MD, and that can probe nanoscale behaviour. So conceptually, MD is rather simple. You move each particle according to the forces on it, again, F equals ma, and you can write that as the gradient of some interaction which we've already seen between particles or molecules or atoms, whatever you're thinking about. And in practice, you don't think about the interaction of every molecule on this one, because that would kill you computationally. You just take some near neighbours and see what forces they are imposing on this particle. So the most common, the simplest potential you can write down is the Lennard-Jones potential, and it has two terms. This one, which we've already seen, which is an attractive part, which goes like 1 over r to the 6, and a repulsive part, which goes like 1 over r to the 12. And this basically stops, or it mimics the fact that atoms, electron shells can't overlap. Okay, so it's like the hard sphere type, the steric part of the interaction. As far as I understand, there's no reason why it should be 12, it's just a convenient number. And you combine these with an appropriate thermostat which keeps some properties constant, such as the temperature or the energy or whatever you're looking at. Okay, so this is short range, so atoms need to distance each other, they can't be too close. This is long range attraction, so everything doesn't fly apart. This joke was a bit better during COVID, but atoms are the ultimate social distancers because they're both sociable, but they shouldn't get too close. Okay, so they're a bit like this woman here, who during COVID was taking great precautions.
What's all that about? Excuse me, love.
She's really germophobic and doesn't want to see. Doesn't want to see.
Are you
Seriously, no, 2 metres, please. Honestly.
No, I'm keeping the 2 metres, but seriously, mate.
Okay. So we use open source software, lamps, and we use. I like using MD as just kind of like a kind of virtual experiment, like a tool just to get some feeling to what's going on there, rather than to pretend we're doing exactly a molecular system. So collaborators like using water quite often because then you can do the red and the white and you can pretend you're having a real world application, but I like argon because it's nice and simple. So these models, they give you everything in some sense, you know, viscosity emerges, surface tension emerges, inertia's there, thermal fluctuations are there, disjoining pressures there, everything's there. But if you want to do even something like 220 nanometer drops coalescing, this is what Sri Hari had to run on the national supercomputer to run a simulation like that. Okay, so they're incredibly computationally expensive. So what we're going to do is we're going to use MD as a virtual experiment, and we're going to do our kind of Navier-Stokes plus some nano stuff. So what we spoke about before, earlier on, we had a film reacting to a change in height and pressure, and now we're going to think about a thin film of liquid on a solid whose height we don't know, and we'd like to find, but we'll see that we do know the pressure at the boundary. Okay, so I showed you all this earlier. Lubrication, we're going to think about no slip, at least in the first instance, of the solid. We have a kinematic equation which Dimitrios talked about yesterday, which says that this is a material surface. We have linearized Young-Laplace equation, so this says that the pressure here, or the pressure jump there really, but it's with respect to 0 in the gas, is the surface tension times the curvature, and in lubrication we have the curvature just given this form. And then we have, again, in lubrication limit, we just find that there's 0 tangential stress on the boundary, so du dz 0. Okay, so we can solve that form. Simplify that system by integrating across the film again, applying the boundary conditions, and then we get this equation, which is like a simplified form of many of the equations we saw yesterday. No electric effects, no inertia, nothing like that, just simply viscous and surface tension terms. Okay, so there's a million different ways to write this. You can write it in terms of flux, which I was doing earlier, or, which we'll see later, you can write it looking like this, like almost like a kind of nonlinear diffusion equation where the m here is called the mobility and depends on, for no slip, it's h cubed over 3 here. In 3D we can extend it, basically these become gradients, we have divergence of the flux, we have the pressure becomes the Laplacian of h, and the mobility is the same. So it's easily extendable. Okay, so what I'm going to talk about is thermal fluctuations, how thermal fluctuations play a role, and then at the end I'm going to try and show you how they matter for the breakup of thin films. So when we think of thermal fluctuations, the first thing we think about is Brownian motion. So column grains moving around in a fluid. And the picture there is, you know, we have this pollen grain with this large particle. It's bombarded constantly by molecules and it has some Brownian motion, Brownian dynamics. So the classical way to describe this is by a Langevin equation, and again we come back to F equals ma. We have here ma on the left, so this is the speed of the particle. We have forces, we have a hydrodynamic force, so if I just have a sphere in Stokes flow, I know that it's given by this expression, 6 pi mu times the radius times the speed of this object. But now I also introduce, I don't want to account for every single collision between the molecule and the big particle. I want to average them all out, not average them all out, account for them in some way as a fluctuating force. Okay, so the simplest way to model these fluctuations, firstly we understand their means should be zero. There shouldn't be some kind of preferential direction in the simplest case. And the correlation, which tells you the relationship between the force at some time and some later time, we assume takes the form of Dirac delta. And that means basically that the fluctuations at time at some instant are unrelated to the fluctuations at the next instant. The delta ij here is a Kronecker delta. That accounts for the fact that the forces in, say, the x direction and the y direction are uncoupled. And so you can see, for example, if I just took the x direction here, this would be essentially the variance. And then the prefactor comes from fluctuation dissipation theorem, which I'm not going to talk about. But essentially that's the prefactor required by the physics. So it always has this term of 2kt times this 6 pi mu a. Okay, what else do I want to say? Okay, so we can make analytic progress if we think about, for example, a particle on a line. It's a relatively simple problem we can look at. So we're not interested in the average position because that's obviously going to be the origin. But we might be interested in the variance or standard deviation. So all I want to do there is show that we can essentially derive an expression for the variance or the standard deviation. The standard deviation we see goes like the square root of time. So this is a typical kind of diffusion type thing, and it gives us this famous Einstein-Smoluchowski relationship, which relates diffusion, which we know something about on the kind of macro scale, to these micro scale things like kT, the energy associated with thermal fluctuations, and the hydrodynamic force. Okay, so what I was going to show you, if it works, is just that. So that's in 1D. In higher dimensions, actually, because the directions are uncoupled, we can just, this is 2 in 1D, 4 in 2D, and 6 in 3D. So I was just going to show you in 2D how that works. So we can solve this equation. In fact, I'm not sure if I solved this one or a slightly simpler one. Relatively easily in MATLAB, just using an extension of forward difference to stochastic problems. So we know how to forward difference things like this. Forward Euler, we just have x minus xt, and then this expression needs a little care to ensure we have the right variance, but hopefully I can oh great, it's on your screen but not mine. Okay, I've spoiled the whole story here by having it up already, but let's play again anyway. Sorry, the problem is I can't actually see it. But so I have a code here, which is about as basic as you can possibly get. So what do I do? So here is the forward Euler type thing. I have x, the next step is x at the previous step times dt, but the random noise brings 1 over the square root of dt from that delta function, and then this random just generates random noise. All I want to show you is that how simply we could reproduce, how the Langevin equation can reproduce this kind of random motion. So I'm just going to do that for, what am I going to do that for? 300 different cases. Okay. They're on my screen but not yours. Okay, so these are the trajectories. So they all start at the origin and they follow some random path. And then the idea of diffusion is I look at the radius of each of these, how far they've gone from the origin, and average over all of them. And that's where I expect this square root type displacement to come in. So here are all the radius of all the individual particles. If I average over all of them, I get this. And this is the analytic square root of 2, 4dt, I think. So, okay, good. So that is kind of in the bulk, if you like. But what I'm going to be interested in is how these thermal fluctuations are going to affect interfaces. So in the early 20th century, there was a lot of work on Brownian motion, kind of things I've started to introduce you to, Einstein, Smoluchowski, Langevin. Smoluchowski realizes that if you have an interface and you have these thermal fluctuations within the bulk, then it's going to affect the interface. And essentially it's going to create waves on the interface. And Mandelstam in 1913 basically derives the properties of these waves. And I'm going to do a slightly simpler version of his derivation. Okay, so let's take some thin film with some length, and let's say for simplicity that it's periodic. So you can see already this is a simulation of a thin film. In our mind, you know, we look at a thin film on a solid, well, it's flat, but in fact, it's not, and it's wobbling around with some waviness due to these thermal fluctuations. This, as we see, the scale of this is a few nanometers, so if you're interested in a cup of water, who cares about a few nanometers? But if you're interested in a film which is 4 nanometers thick, then things might be interesting. Okay, so what we're going to do is we're going to take this film, it has some average height, h0, and we're going to add a perturbation to account for these waves. Because it's periodic, we can expand in Fourier modes, and the game is going to be, what are these coefficients? I mean, that's always the game, but we might expect their average is going to be 0, because this is flat, it's fluctuating around something. So we might be interested in their standard deviation or their variance. So everything is now stochastic. So we can apply an energetic argument, and we can say that it costs some energy to increase the surface area of this film, and the energy it will cost. So here I'm doing what I call quasi 2D. So what that means in practice is molecular dynamics is always inherently 3D, but I want to compare to a 2D theory just to make things as simple as possible for a start. So I have a very thin slab into the page and periodic in that direction, so not much happens into the page basically, but I do need to account for it when I average things. So in 3D I have this, the area of this surface is basically the distance into the page times the arc length formula, and if dh/dx is small, which I'm going to assume it is, I can get this expression, which is the extra area created, the extra energy due to the extra area, so this is surface tension. Stuff this in here and integrate, still within my mathematical skills, and I find out the energy associated with each mode. So, for example, larger n, which means shorter wavelengths, they have higher energy, because surface tension doesn't like this highly wiggly type surface. Then I use equipartition of energy, which basically says that each of these modes has to have average energy of kT over 2. And that, from that, I can back out what the variance of these coefficients are. Okay, so it has this form. What's of interest? So we have this LT. This is what I call thermal length scale. This is crudely the amplitude of these waves. So it's kT, because kT is thermal fluctuations. It's trying to push the interface in all sorts of random directions, divided by surface tension, because surface tension wants to flatten this interface. And it's small. Right? 0.2 nanometers for water, that's a bad case because surface tension is high, but it's always of this kind of nanometer scale. What else? Well, the longer the film, the larger these things. What's that? Because I can fit more waves in, right? So the longer this is, the more waves I can fit in. N squared, that just accounts for the fact that the amplitude of small, the amplitude of short wavelength modes is going to be small because they cost a lot of energy. So this is, the long wavelength modes will typically dominate. So one of the things we calculate quite a lot is the spectrum, which has this expression. So it's Fourier transform of the perturbation, mod squared, average square rooted. So it looks horrendous. Crudely, you can think of it as being the amount, the amplitude, the size, the power of a given mode, k, at some time. So we've done already, we found this in equilibrium, in thermal equilibrium. And we can rewrite that as this for the spectrum. So it goes like 1 over k. So as we expect, large wave numbers, which is short wavelengths, have small amplitude or small power, if you like. And this is what's known as the period wave theory. So it's kind of like the result Mandelstam derived 100 years ago. So we can run molecular dynamics now with multiple realizations, starting with a flat interface like this, and watch these waves develop in time and see, for example, do they approach this expression? Well, this is this expression here, and we see that as time grows, the molecular simulations start to approach this equilibrium case. And if I have time, what I'm going to talk about later is how we do the dynamics of this process, which is obviously going to need a dynamic theory. So this is all based in equilibrium. Okay. So we're getting there. So that was all in equilibrium, but I want to solve dynamic problems. Okay? So I need a theory that incorporates noise into some momentum equations, for example, and that is what's called fluctuating hydrodynamics. So fluctuating hydrodynamics came from the work of Landau and Lifshitz, and hopefully I mean, it looks horrendous, but I've introduced you already to the Longevin equation, and the idea there is, well, we've got hydrodynamics, and let's just add a fluctuating force with the right prefactor and hope that mimics the noise. And that is exactly what this is. This is just a fluctuating force, and the force you write in terms of a stress tensor, fluctuating stress tensor. Things are worse now because it's a tensor, not a vector. But the structure is quite similar. We have these Kronecker deltas. The noise is uncorrelated in space and time now. And we have the prefactor. And again, we have that the mean of this thing better be 0. So there's no preferential direction. Okay. So fluctuating hydrodynamics is growing in use and interest. There's a lot of work in America going on in various cases, and it's always the case where you want to solve a kind of macroscopic flow, but it transpires that thermal fluctuations matter. So there is somewhere where MD is just too painful to do, and so you want to incorporate fluctuations into a macroscopic theory, and this is then the way to go. Okay. What's nice, fortunate for us, is that around 20 years ago, Grun derived a thin film equation for fluctuating hydrodynamics. So this is the thin film equation we saw earlier. The HDT is divergence of this flux, which is gradient pressure. And essentially, you have an additional term which comes from the noise. And this noise has some correlations, as we've seen already. And obviously, going from, I mean, Navier-Stokes is nasty enough as it is on its own. Adding fluctuations to it makes it a bit horrendous. So going back to something where we're just solving for the height as a function of some variables is much simpler. Oops. So for our quasi 2D case, because we want to compare to the MD, we have dH dt is d by dx of this term which we had before, plus a noise term, so this is the random noise in here, with the appropriate free factor, and we'll have a play with that. So, where we started was the simplest possible thing. So we have this film. We're not thinking about rupture quite yet. We're thinking, how does it develop that equilibrium? So I showed you, we start with this kind of slightly fake initial condition of a very flat film, and then time progresses and these waves grow to some equilibrium state. So what Yixin's PhD was all about was trying to describe the development of these waves. Okay. So we have this thin film equation, which looks like this. And what we'd like to do is understand how these waves develop. And so we can start to do all of the kind of classical things we would do, similar to the things Dimitrios was talking about yesterday. We just take some height and we perturb it with something small. Okay. But things are going to be a bit more complicated because this is now stochastic. So we perturb it with something small, we linearize because dH is much smaller than the film height. And then we put this thing into Fourier space. So we Fourier transform across this, and we get the following expression. This is something which is not particularly hard to analyze. We have this omega, which is like a growth rate, but you can see it's always going to be negative, so it's always going to decay. And we can arrive at that thing I talked about earlier, which is the spectrum. So this is, how does this work? So what we had earlier was part of this. This depends on the initial shape which we put in, but we're essentially going to start with a flat film, so I think this term will be 0. And then there's a time dependence, so it's going to show us how this spectrum develops in time. Okay? We didn't derive this first, this was by Mecker and Rauscher in 2005. So this now is the spectrum at a given time and how it depends on k, the wave number. Okay. To get this MD curve, you maybe have to run 10 simulations on average. And this line is just straight from this analytic theory. Okay. So we do this for different times, and it's okay. It's on the right page. What's interesting is, compared to classical theories, here the fastest growing mode changes in time, which is kind of a non-classical effect. But as you can see, the agreement isn't great. So the first thing that Yixin tried, for things like argon in molecular dynamics, you actually have a huge amount of slip between the liquid and the solid. When I say huge, I mean a few nanometers. So the first thing to do was very similar to what I was doing in gas kinetic effects, but now a liquid in contact with a solid, use a Navier condition instead of a no slip. So if L is 0, that's no slip, and if L is a few nanometers, you have a slip condition which modifies the mobility to look like this. So that was versus no slip, and slip fixes all our problems. This isn't just some free parameter. What we do is we run Poiseuille flow, Couette flow in the MD, and from that you can extract the slip length, and then you use it in these simulations independently. What you notice is that here the agreement still isn't great. So this is wave numbers around 1. Any idea why that might not be so good? Sorry?
Surface tension?
No, not quite, because surface tension is in both the theory and the MD. So we've taken a thin film model where we assume everything's thin, the HDX is small, all that stuff. A wave number one basically breaks that assumption, right? These small, these around here need to be described by Stokes flow rather than lubrication. And we've done that as well, and then you can continue this game. Okay. So the question I started with, and the thing we're working on recently, is can a wave induce rupture? So at the moment I've shown you this picture where we have these waves wiggling around on top of this film. And the question is, if I wait long enough, will one of these waves rupture? Will the dip of one of these waves reach the solid and create a hole? Okay? Both will that happen, and how on earth am I going to model that? Okay, so a lot of work was done on this in the 90s and the noughties. Some famous papers in Science and Nature, where they saw these are holes here forming in films. So here I think they freeze the metallic films and look at the holes that are formed. Here these are in polymer films, and they can see using AFM. So how are we going to model this? Well, we're going to go back to our thin film equation. You're now all experts in disjoining pressures, so again you recognise this. It's slightly different because we have a solid liquid vapor system rather than a solid vapor liquid system. So you have a slightly different expression in here. And what I'm going to do is I'm going to non-dimensionalise with a very specific height. This height is the height at which, below which, disjoining pressure will rupture this film. So I've already mentioned that this can cause instabilities, and it only causes instabilities when we're below this height. So what I'm going to do is I'm going to choose that height to non-dimensionalise with, so that what I'll have is in this dimensionless system, I'll have heights less than 1 are linearly unstable, heights greater than 1 are linearly stable. Okay, so I might have skipped a few bits here, but this is what I taught you earlier, where we can find, so I was going to explain here where this linear stability comes from. So here we have the film, we have the disjoining pressure which I just mentioned, and we know from before that long wavelength instabilities are possible. So that's the term that I just mentioned, which shouldn't have been there before, spoiled the entire narrative, but never mind. And this is when we non-dimensionalise with this height which I just mentioned. Okay, so now for heights less than 1, this thing is linearly, I mentioned this height's less than 1, this thing is linearly unstable. Okay, so what do we see in experiments? So a very typical experimental image looks like this. This is what's called spinodal rupture. And the picture here is that the film is linearly unstable, so waves are growing everywhere, and they touch down with some characteristic wavelength, which is the distance between holes, very crudely, and create dry spots. Okay? So lots is known about linear instability in films. But what's been seen is that we not only see linear instability, but we also see cases where the film is stable but still ruptures. The film is linearly stable but still ruptures. And the experimentalists called this the thermal regime. So here, the picture is all these waves growing, all touching down roughly at the same time. Here, you watch the experiments, random holes appear in random places at random times. Okay, so that's why they thought it was a thermal mechanism which was at play. Mathematically, this is linearly unstable, and this is linearly stable. And this is the one we're going to be interested in. So it's, again, the same question. Linearly stable film, lots of fluctuations on the interface. Can one of these create a hole? And how long does that take? So the first thing we did was just throw a molecular dynamics simulation at this kind of problem and see what we could find. So we know the height at which this thing is unstable, and we can run an MD simulation for a case where H0 is less than 1. And this is like the spinodal type rupture. So there's like a characteristic wavelength, if you like, roughly, and you see multiple holes forming. It's all linearly unstable. Now we take a film which is linearly stable, but we'll still see rupture. Okay? So this is like the thermal regime. This is waves growing all over the place, and eventually a longish one grows big enough to create a single hole. Okay, so from those simulations we can average over maybe 10 different simulations, look at the shape of the interface when it breaks up. So this is typical of spinodal rupture. It's a very localized rupture. And for the thermal rupture, you basically, because you have to conserve mass, you have to pick the whole film up on the outside for it to create one hole in the middle. Okay. And then
James, quick question. The time scale at which it happens, are they different? Very different?
very different. So that's, you teed me up nicely, Demetrios.
Okay.
I feel like I should come over to that one now, but so this is spinodal. I've got to answer your questions. I'm going to come to this. This is spinodal. This is the time, average time. Spinodal is very fast, and then thermal is very slow, and it's exponential, in fact. Okay. So the whole game we want to play now is this is some thermally activated process. So we think, oh, it probably should be exponential, and I fit the prefactor and the power, and it is exponential. But obviously we'd like a theory which tells us what's the prefactor and what's the exponent. So the key point here really is you increase the film by 10%, 20, 30% above this critical height, and the time goes crazy. So it's one of those where maybe, you know, if your film height is 3 times this height, it will take like longer than the time of the universe to rupture or something like that. So it's a very delicate kind of problem. Okay, so let's start. Yes.
Question. Can these holes, can they heal in a way? Or do you observe that in the simulations once they...
I haven't, no. But it's an interesting question. I mean, for the single hole, it seems unlikely, but for the multiple holes, I could imagine maybe they'll interact and do lots of things.
I was thinking of cavitation, that sometimes you have like nano bubbles forming spontaneously in the gas, but then they heal so quickly that eventually they disappear.
Yes. I also wonder if we'd have even seen that, because probably we were looking for the holes, so they might have healed, and we didn't even see them healing, if that makes sense. So it's an interesting question. Thank you. Okay, so this is our stochastic thin film equation, and then we non-dimensionalize it. This epsilon is now like the strength of the noise, and at first instance it looks like it's the thermal length scale divided by the height of the film. Okay, which makes sense. It's the amplitude of these waves divided by the film height. So if it's very noisy, these waves are going to be comparable to the height of the film. So the first thing we did is we just solved this stochastic PDE in a slightly simpler case, multiple times average compared to the MD. And the agreement is kind of remarkable. There's nothing here to fit. We know what the surface tension is, we know what the viscosity is, we know what KT is, we can't fiddle with them. And the agreement is good. And we capture this qualitative trend that spinodal, linearly unstable is very localized, linearly stable is much more of a kind of global event. Okay, and if we look at the time scales, so now we're on a semi-logarithmic plot, just tells you how quickly these time scales grow. This is the thermal regime, things happen very quickly. This is spinodal, this is thermal, things happen very slowly here. For here, this time scale 1, for each simulation, which is only 1D, you need to take about 10, 100 million time steps. And then you need to average that over 100 different realizations. And so things start getting very painful, even in 1D, very quickly. So the thought was, can we extend this using some clever theory? And that's what I'm going to talk about at the end. So the clever theory is the theory of rare events. So the stuff I've told you so far I didn't know much about. The stuff I'm telling you now I know nothing about in comparison. But fortunately, at Warwick, Tobias Grafka is an absolute expert in rare events and stochastic processes. And a lot of his previous work has been on things like this, so like rogue ocean waves. Okay? So there, you know, the question is, you sit on an oil rig, you sit there for 15 years, nothing happens, and then suddenly you get wiped out by a rogue wave. How to predict those kinds of rare events. And the idea was, can we apply those ideas to nanoflows? Okay, so this is our system I've already shown you. And the important thing, so Tobias tells me, is that you can write this as a stochastic gradient flow. So what does that mean? That means the HTT is minus the gradient of an energy. So this energy is what you'd expect it to be. It contains the surface tension, it contains the disjoining pressure. And these are operators now. So this is the mobility operator, which looks like this, and the noise operator, which has a certain relation to the mobility, looks like this. Has to look like that, essentially. So what this whole rare event theory tells us, or what Tobias tells me, is that when the noise is small, we can apply this theory of rare events. That makes sense, right? I mean, if the noise is large, these ruptures, these events are going to happen all the time. If the noise is small, then they are indeed going to be rare. So the game we have to play is we have to find the saddle point of this energy, and if we can find that, we can find the time it takes the rupture, which is the energy it takes to get to the saddle point minus the initial energy divided by epsilon. This is like KT basically. So how you want to think about this is you have this film which is stable. You push it down a bit, still stable. Push it down a bit, still stable. Push it down a bit more, it's unstable. And that's the saddle point you want to find. Obviously it's slightly complicated. You don't know the shape. I mean, I did this, but I don't know if it's that shape or if it's some other shape. So it's not hard and it's not trivial, essentially. Okay, and this thing is independent of mobility, but this prefactor isn't, and I'll talk about that in a minute. There is a limiting case we can consider, which is where the disjoining pressure is negligible. So it's kind of like a thick film where disjoining pressure is weak. And it's really nice. Here we can just derive the solution, and it's a parabola, and the energy is this. In this case, we can then put this energy into here, and we see that the exponent, what goes in here, is this, which is a half h0 over sigma squared, and sigma is the standard deviation. So it tells us that what goes in here is basically the height of the film divided by the standard deviation of the fluctuations squared. So, for example, if the fluctuation is very, very weak, this is large, and the time is huge, which is intuitive. But in the general case, we need to solve this analytically. Solve this numerically, sorry. So this is what the numerical profiles look like. So if my height is just a little bit stable, then I don't have to push it very far to reach the saddle point. If it's very stable, notice it's only 2 times the film height, I have to push it a long, long way down here to reach the saddle point. So it costs a lot of energy, and it's more unlikely. Okay, so these were the shapes I showed you before, and this is my very mathematical thing that this is parabolic-ish. These rare events are extremely hard to compute because they take a long, long time. That's the whole point of using rare event theory. So to actually derive, to do MD, for example, in the rare event case is essentially impossible. We can only ever get towards it, if you like. Okay, so what we're going to do is we're going to simply take this expression for the rare event, which is this line here, and I'm going to fit the prefactor so that this black line starts to kind of join this green line. Okay, so that was the C I showed you earlier. I just fit it, and things look okay-ish. This is the limiting case here, so you can see it's starting to tend towards this as we get very thick films, but it's not there yet. I was absolutely delighted that this green line was anywhere near this black line. I'm easily pleased, obviously. What Jingbang did, who is my PhD student, who's far more mathematically competent than I am, is with Tobias, he went away and derived analytically what this prefactor should be. And it's not the simplest expression you've ever seen. It involves Hessians and determinants, and there's an eigenvalue in there, various things. But it is an analytic expression which you can put your computational solution into for the saddle point and compute it, and you know what C is. And if you do that, then this green line goes here. And now there's no fitting, it's just this formula. So it's like some kind of a miracle, because it's a rare event, so it should only really apply down here where the event's rare, but somehow it kind of curves around. After here it gives absolute garbage, but we should only expect it to apply over here anyway. So now there's a fully predictive expression for the time it takes to break up a film, which is pretty easy to, I mean, it's like seconds to compute on a computer rather than more time. We can also look at check it is indeed a rare event. So if we have, this is the probability density of breakup times. So spinodal, what happens is it takes some time for the fluctuations to grow, and then it ruptures relatively quickly, and there's not much chance of it being down here. For the rare event, it's exponentially distributed. So the most likely time is kind of the start, but then you have this exponential distribution with tail down like this. And that means it's a Poisson process, which is indicative of a rare event. We can also look at the different parameters involved. So no massive surprises there. If we increase the noise strength, this happens faster. If we increase the slip, it happens faster. And that's because slip basically means when a hole starts to form, you can push, fluid is pushed out much easier, for the same reasons as it was with the kinetic effect, and so rupture happens much quicker. Okay. So this is all fine, but it tells us nothing about the experiments really, because the experiments are inherently a 3D thing, and so to do it with lubrication, you'd need 2D lubrication rather than 1D, which I've been using. So we've only touched upon the very edge of looking at this. These are the experiments that were initially published showing the formation of films, of holes, and these are some of the simulations which were done with fine elements. And I was desperate to try and reproduce these because they look really cool, basically. So these are called satellite holes. So what happens is one hole forms, and as a result of one hole forming, you get multiple holes forming around it. Okay, so these are satellite holes. And I was desperate to try to reproduce this. So I have a code which solves thin film equations. I never know whether it's called 2D or 3D, like in real life. So it's 3D real life, but 2D equations. And I thought, okay, well, I'll start off by just starting with a film and putting a random perturbation on all over it and seeing what happens. So it broke up, didn't look anything like this. I thought, oh, okay, well, I need to make sure there's a hole in the middle. So I put a hole in the middle, and then I ran it. And it formed this perfect hole which just opened up with none of these satellites. And then I read the paper for about the 75th time. It says, as initial data, we took a slightly corrugated film with a depression in the centre. So then I had a depression in the centre with random noise over the top of exactly the right strength. And I had a happy morning. So, indeed, if you do that, this is with no thermal fluctuations. This is purely deterministic, apart from the initial condition, which contains some perturbation. And it looks a bit like what it should. But it's kind of completely fake in some sense, because the whole thing just depends on this very specific initial condition which has no physics in it. So physically, thermal fluctuations are key. Right? So there are two games we can play here. Game one is we can put some kind of equilibrium state as a thermal fluctuation into the initial condition. Game two is we can start doing it properly and actually having thermal fluctuations built into the thin film equation. So we've done some MD in 3D. There, it's also very difficult. You've seen how sensitive the time it takes to rupture is on the height of the film. And that makes it really difficult to do MD, because you do a film of like 4 nanometers thick and it never ruptures, and then you do 3 nanometers and it ruptures instantly. It's that kind of delicate balance. So we'd like to compare two experiments. We'd like to consider more complex solids, such as the ones I showed you before, where they essentially modify the disjoining pressure by having multiple layers of solid. Okay, so that's the film stuff. Where all this started was actually with jets, which is the thing I'd like to talk about in the last few minutes. I think I'm going to finish early, nobody's going to be unhappy about it. Have I got till 1? Okay, well, I'll finish early, so you'll all be happy. So Cheng Shi was the first PhD student to work on this, and he was the person who really understood, for a start, that thermal fluctuations are playing a big role in the molecular dynamics that we're doing. So the question, we took a very kind of classical problem, infinitely long cylinder, which is never infinitely long in MD, but is long and periodic, and, whoops, that video? Okay, so it's deciding it doesn't want to play, but essentially you can imagine this. What you should imagine is exactly what it would look like macroscopically, essentially, which is a jet breaking, waves growing on a jet. In fact, I've got the pictures here. So waves grow, and eventually it breaks into drops, and it looks remarkably like you would see on a macroscopic experiment. So to compare MD to theory, again, we looked at the spectrum. So this is, again, the wave number against the spectrum and how it develops in time. So these are waves growing in time as the kind of waves grow on the surface of this cylinder. You also notice that they actually remain relatively axisymmetric. If we then calculate the spectrum from the deterministic model, it's miles away. Okay? So this is lubrication equation, radial plateau, and it's down here. So this is the same picture we see quite often, and that's that one of the main roles that fluctuations have is to speed up an instability. Okay, so classical instability, it's this exponential growth, but compared to having a bump from thermal fluctuations, it's actually relatively slow. What we then did is we took the stochastic model, we took the lubrication equations essentially in cylindrical coordinates rather than in planar, which I've shown you so far, which is the classic kind of model. And there you can see we model the growth much, much better. Okay, so this was published. I'm not sure if I have. Okay, so this was a front cover in JFM, which Cheng Shi managed to do, which we were all very happy about. And so here you see exactly, this starts to look exactly like the macroscopic case, right, where you have jets and you have satellite drops and all the things you expect to see, but it happens a lot faster because the fluctuations speed up this instability. The thought there was very similar to the thin film stuff. Given these fluctuations matter, maybe we can rupture linearly stable jets. They're not really jets, they're more like fat threads. So what we know classically is we have this plateau stability criterion, which says that if we have a sufficiently fat cylinder of fluid, it should be stable. And yet if we look in MD, we see that these fat cylinders still break up. And that's because we have this kind of perfect storm of fluctuations which eventually will break it. And this is where we actually started everything. And we calculated in MD the waiting time, how long it takes for this rupture to occur, average over multiple things, and plotted it against, this is the fatness of the cylinder essentially. So when it's very fat, it's very, very stable. It takes much longer to rupture. And down here it's linearly unstable, it's all Rayleigh, it's all well known. What we haven't done yet is apply the rare event theory to this, to predict this. So that's kind of an open problem. We did the thin films and I thought, oh, I'll just bash this out in the morning because I know exactly how to do it now. And it was a mess, so I need to come back to it and try this again. Okay, so the final piece of the jigsaw is drop coalescence. So we've already looked at drop coalescence in some sense with drop-drop collisions, but now essentially we're going to look at nanodrops. And the situation with nanodrops is rather different because if you see here, can anyone see the gas? This is the gas here, right? So it's not going to have a huge influence on these two drops. This is a water vapor system. You can see the density of the water vapor is just negligible. So it's kind of interesting because all of this stuff started with a completely different aim. The aim was, kind of my background was in looking at singularities in free surface flows. So I know there's a singularity in coalescence problems. I know there's a singularity in jet problems. So I was thinking, let's look at those singularities. And what we found was that other things were as interesting, or maybe even more interesting. So here, my thought was, well, let's bring two nanodrops together and we'll look at what's going on here where classically everything's singular. And what you find is that you bring two nanodrops together and they don't meet on the centre. So, problems from the outset. And the reason they don't, and in fact they can join in multiple places, is because nanodrops have fluctuations all the way around them. So that's what a nanodrop looks like. Our classical picture of it being a sphere or a circle, well, it's a sphere with perturbations on it. Waves here travelling all the way around this surface with some properties. So if I took an instantaneous snapshot, it would look like that. It wouldn't be a circle. If I averaged over multiple snapshots, then I get back to a circle. So on average, it's the shape we expect, but it has some waves. They have some characteristic wavelength, and you can already see where all this is kind of going. So the theory of the off-center contact was worked out in this article. Okay, so good news, I finished this one 15 minutes early, having finished 5 minutes later than the last one. Any questions at all?
These sample solutions,
yeah.
Are they always kind of weak solutions of the equations? And they always attach down, that's right. I mean, I saw you got a parabola. And that is the minimal surface energy solution. But if you disallow the film to attach, then you won't get that.
Precisely. So the parabola isn't actually a saddle. The parabola occurs when you have no disjoining pressure. The saddles occur when you have disjoining pressure, and then they approach that. So none of them touch down.
Okay. Because there's actually a disjoining.
Exactly. Yeah. So you just need to push it far enough that disjoining pressure wants to pull it in. And that's what the thing tells you. So there's various saddle finding techniques.
So what would happen for a cylinder? Then I guess you've got a valve.
Yes, exactly. So for The interesting case is, of course, the linearly stable one. And then, so my thought was I'll just write this down in polar coordinates, in cylindrical polars, and I'll bash out the saddle points. And I did that 6 months ago. I can't remember why it didn't work, but it didn't work. I think there is an analytic solution there as well, which probably may also be a can't be parabolic. It's more complicated because there are R's flying around, or 1 over R's.
I have another one.
Is that better?
Of course. I think it was in the previous talk, when you did the Fourier series coefficients, and you average them, the AN square
Yes.
average, that was 1 over n squared.
Yes.
Does that mean that the average, the absolute AN average is 1 over n?
It might be. Yes, it is, yeah, because it's 1 over k. Yeah.
So then I guess I was a bit confused, because then to derive that you had to use the energy of the gradient.
Yes.
But then the gradient doesn't really exist.
Yeah,
Right?
precisely, yeah.
So
That could be, yeah, it's an interesting question actually. So I mean, we saw that in the dynamics where lubrication died and we had to use Stokes. And in fact, we showed that you can actually relatively easily do dispersion and things like that for Stokes in these cases. But the improved lubrication, you never thought about this, but yeah, you're right. It violates everything in that dynamic. Yeah.
right. Thank you.
Okay, if some of you are teaching science, please do this, or if somebody else come, please ask them to come to me. And Lucian Junk, could you please come to me? Yeah. Okay.